In this last video in the series on kinetics, we want to look at the role of a catalyst. So we saw in the previous video when we were looking at Michaelis-Menten kinetics, we had mention of enzymes. Enzymes are biological catalysts, but we never actually looked at catalysts themselves. It was just a label that we used in the Michaelis-Menten kinetics videos. So now I want to actually spend a few minutes looking at catalysts. So to preface looking at catalysts, though, I want to look at conservation of energy a little bit. The reason is I think it's easy to make a mistake when you look at catalysts. Catalysts seem to make energy disappear. They don't really make energy disappear. They redistribute it a little bit. But in some of the diagrams you'll see in textbooks, it looks like they violate conservation of energy, which they don't. So I want to preface this video with a quick talk about conservation of energy. Okay, so let's look at the one-dimensional case. We'll look at the x direction only, but you could scale up to 3 dimensions. So we'll take an expression, a mathematical expression for conservation of energy. So total energy here I've called U. That changes with time. So here this dot just means the change in U with time. It's just a quicker way to write it. So the change in total energy per unit time is equal to the sum of the change in kinetic energy per unit time plus the change in potential energy per unit time. And if we sum that all up, it should equal 0, which means it doesn't change with time. So this is an expression of conservation of energy. Let's look at the kinetic energy term for a second. The kinetic energy term we know is m, probably need to annotate here. We saw in a previous video the kinetic energy is mv squared over 2. Now, the mass and the number 2 won't change with time, but what could change with time, what is changing with time, is velocity squared. So we're going to focus on that and just look at velocity squared changing with time. And we're going to use the product rule. So here we've got a product, we've got V multiplied by V, so that's a product. So we use the product rule. And the product rule says take one member of the product and ignore it, and then apply the change to the other member. So we've separated the two V's in our product. So it's V multiplied by dV by dt. And then we do the same for the other one. So if you like, let's say V1 is one of the V's. So let's say this equals V1, V2. Then we ignore V1 and we apply the d by dt to V2. And then we ignore V2 and we apply d by dt to V1. Okay, so that's the product rule. And now you can see that we just have 2 copies of the same thing. So we have 2 multiples of V dV because V1 and V2 are the same thing. We notice that dV by dt we can write as V dot because we are summarizing the d by dt with a dot. So we've got 2V V dot. Okay. If we put the constants back in now, the mass and the number 2, which remember we ignored because they were constants, we put those back in. We've got the mass and the 2. Well, the 2 will cancel the 2 that we had here, and we're just left with mv v dot. Well, that v dot is just acceleration, right? So it's the change in velocity per unit time. So we finally got the change in kinetic energy per unit time is equal to mass, velocity, acceleration. Okay, so now we're going to do the same similar calculation for potential energy. We'll add them together and they should equal 0. Okay, so we can see here, if we look at the change per unit time of potential energy, well, potential energy is not time sensitive, it's location sensitive. So we have to use the chain rule to make a version of it, or to express it with a sensitivity to time. So we're going to use what's known as the chain rule here. So out the box, potential energy is sensitive to location, x. But if I want to set it equal or express it sensitive to time, at least falsely express it that way, then I just multiply by dx by dt. So you can think that the dx would cancel. It doesn't really cancel, but it kind of looks like it would. And then we have dpe by dt. Well, we know that dx by dt is velocity, the change in position dx per unit time. Dt is just velocity. So we have this expression now for the change in potential energy. Okay. So now we're going to plug it back in. We'll see what we have. So let me scroll down. Okay, so far we've said that our statement was that the total change in energy per unit time is the sum of these two changes in energy per unit time, which must be 0. Well, we know that kinetic energy changing with time is MVA, mass, velocity, acceleration. And we've just seen that the change in potential energy per unit time is the change in potential energy per unit location multiplied by velocity. We notice that both terms have velocity in common, so we can factor out velocity, and we get ma from the kinetic energy term and dpe by dx from the potential energy term. Well, we know that the definition of force is the negative of this term. So by definition, the force at a location x is the negative of the change in potential energy at that location per unit x. So we essentially have this u dot, the change in total energy, is v. We've got our ma from here, and then we can replace this plus term here from minus force term here. We know from Newton's second law the force is mass times acceleration, or minus force therefore is minus mass times acceleration. So we've essentially got a positive force minus a positive force, which is 0. So indeed, we can see that energy is conserved, at least in one-dimensional case. Okay, so that's important. We knew that, but we want to keep that in mind when we look at catalysis in a second. Now, the way we've looked at conservation of energy here is a pretty limited way. So let's look at a more robust way. And again, the reason for doing this ahead of a few words on catalysis is to really drive home the fact that energy can't be created nor destroyed. So to keep that in mind before we look at catalysis. So let's look at something a bit more robust called the continuity equation. Continuity equations describe the transport of an extensive quantity in general, and the extensive quantity we want to refer to here is energy. Continuity equations are a stronger version of conservation laws, and we'll see why in a second. The weaker version, the conservation law that I saw that we just looked at previously, just says that energy is conserved, but it doesn't do anything to, it says that overall energy is conserved, but it's not a local phenomenon. So the continuity equation is a local version of the same thing. And because it's local, it prevents teleportation. So it doesn't allow energy to just disappear or teleport. It looks at the immediate environment around every energy source, and it says that that can't disappear either. So regular conservation of energy allows for teleportation of energy, continuity doesn't. So that's why it's a bit more robust. So whereas we've just seen the weakest statement, so I called it U in the previous page. Here I'm calling it E, but it's the same thing. So E and U are the same thing here. It doesn't change with time. The strongest statement is this. This is the continuity, or a continuity equation for energy, that the temporal change in the energy density here, this lowercase u is energy density, or energy per unit volume. So the change in the energy density plus this divergence, del dot, the symbol here is called del. Where here del just means d by dx plus d by dy plus d by dz. So it looks at 3 dimensions, the change in the 3 coordinate axes, x, y, and z. So the divergence, or the spreading out of an energy flux, which is an energy per unit area time. So if you think about this, the sum of these two terms is 0. And that makes sense. If energy can't teleport, teleportate's not a real word. If energy can't teleport, you have to account for its local distribution or local transportation at every point in space. Then it makes sense that it wouldn't be allowed. The density, the energy per unit, any per unit volume, that if you account for that changing with time, so it can change with time, but if you measure how much it changes with time, and you also look at its divergence, the sum of those two phenomena must sum to 0. So that totally it takes care of any possible teleportation, because clearly teleportation would violate that expression. Okay, don't want to say anything more about the continuity equation at this point, so it just hopefully drills into my students' heads that energy can't be created or destroyed. With that, let's now cautiously look at what a catalyst does. Okay, so catalysts facilitate reactions. You can actually use catalysts to speed up reactions or to slow them down if that's the goal. Catalysts provide an alternate pathway for a reaction to occur with a lower activation energy, and consequentially, the reaction can happen at a faster rate. Let's look at a pathway here. So if you imagine, and this is the danger, this is what I wanted to alert you to. If we imagine the uncatalyzed path up here, it has this activation energy barrier here. So this is without a catalyst. So there's a large energy obstacle. Now with a catalyst, it's broken up into pieces, but it looks like energy is lost, and it really isn't. So here we've got an EA1, and here we've got an EA2. So these are much more manageable. You know, if you were a proverbial person and you had to go over these obstacles, you could probably get to the end of your obstacle course at a much faster rate than if you were somebody that had to go all the way over this one to get here. You would imagine that the red person would get here last and the blue person would get here first. Right, that would be a reasonable expectation. But importantly, we have no loss of energy. We just have redistribution of energy. Okay. So consider an example. So ozone is decomposed with sunlight to give oxygen and an oxygen radical. Ozone can then react with that oxygen radical to regenerate oxygen again. So overall, if we ignore the oxygen radical and we basically add these two equations together, we get an overall change for ozone. So 2 molecules of ozone can change into 3 molecules of oxygen. And the activation energy here of the rate determining step, which is the overall step, the slow step, we're told is 17.7 kilojoules. Okay. If we catalyze that process, and back in the 80s, it was realized that chlorofluorocarbons, or CFCs, were a potent catalyzer of ozone decomposition. So we have here examples of chlorofluorocarbons, which are stable in the atmosphere and can lead to ozone degradation in the ozone, the hole in the ozone layer. Then let's say we have a catalysis here. Ultimately, it would lower the activation energy for the process from 17, I think we said it was 17.7 kilojoules per mole, down to 2.2 kilojoules per mole. So here we would have, now notably here, we notice that the activation energy is not just the first one, it's the highest one. So we've gone from this value of 17.7 uncatalyzed down to 2.2 with the presence of a catalyst. And obviously this process is going to dominate. We don't have to go up here. If the goal is to get down to the product side oxygen, we don't have to scale 17.7 kilojoules of energy. We can just scale 2.2 kilojoules of energy. So in the 80s and 90s, it was decided to remove CFCs from consumer products and prevent the catalysis of ozone in the atmosphere. Catalysts come in flavors. You can have homogeneous catalysts, which we'll look at much later on in the course when we look at coordination compounds, because homogeneous catalysts, for the most part, are coordination compounds. Homogeneous just means they're in the same phase as the reactants and products. And heterogeneous catalysts, which pretty much we won't look at all other than to mention them. And they are in a different phase. And there are many examples you can look at in any textbook about examples of heterogeneous catalysts. And, you know, stemming from what we said about Michaelis-Menten mechanism that governs most of a vast majority of catalytic pathways in biology and biochemistry, I can't think of any examples that are not. So I would confidently say that all metabolic processes are catalyzed, and the vast majority of processes industrially are catalyzed also. So there's a massive multi-billion and soon to be, if not already, $1 trillion industry in catalysts. The only other thing, so my notes also go on with some extra reading for my students. The only thing I would comment on in this video is just to highlight one of the slides here. So in my reading, I have my students do a bit of extra reading. If you see something like this in a reaction profile, where in the presence of a catalyst, so the catalyst here obviously would take this uncatalyzed activation energy and split it up into these more manageable steps. Look at this here. Anytime this dips below the energy of the product, this is where you've essentially killed the catalyst. So you have killed your catalyst. So this is effectively a dead catalyst. And the problem is you've formed a thermodynamically stable complex with the catalyst. That's a no-no. You've now stopped the catalyst becoming a catalyst. So I wanted to point that feature out if you see it in a diagram. Also, I want to point out one more feature on this video. And that is the turnover frequency. Obviously, a catalyst works at a substoichiometric quantity. So Here they've called the catalyst Q. So the catalyst, let's call it Q. Why not C? Who knows? But I never wrote this. So let's say the catalyst is Q. And the concentration of the catalyst, we want to be a lot less than a stoichiometric amount. So we don't want mole ratios of catalysts. We want a tiny fraction of a catalyst. We want a catalyst to be very hardworking. And one of the ways we can gauge how hardworking the catalyst is by its turnover frequency, N, or turnover number. So the turnover number is going to give us our rate. So N is going to be the reaction rate, which they've called V here, divided by the concentration of catalyst. So if we have a good turnover number, a high turnover number, which can be in the billions, so you can have N, 10 to the 9 are possible. We want a high rate for a relatively small concentration of catalyst. Okay, and that will conclude this kinetics video.